All right, we've seen how definite integrals can be used to find the area under some curve f from some point to another point. So we've got this kind of a setup so far. We've got our axes here, and if we have some sort of a point a up to b, and we have some crazy function f, then what we can do is look at this area from an x value a up to some other x value b, and if we shade this in, this area under our curve really is just our integral from a to b. It's the definite integral here. So we'll say this is our integral from a to b of f of x dx, which we know using the fundamental theorem of calculus is the antiderivative, capital F of b, minus the antiderivative, capital F of a. So we plug in our top number and plug in our bottom number and subtract those two answers, and then we're good to go. The only thing that we have to worry about is being careful about the signs, because we know that if we dip below the x-axis, maybe now we've got a negative area, and so we'll just keep an eye on all that stuff. There's really not much more to finding area under a curve, but the question that we want to ask is, what about finding the area between two curves? What if we look at something like this instead, where we have our axes, and now instead of one function, we have two functions. So maybe here's my function f, and I've got some other function down here, g, and I'm going to go from an x value a up to an x value b, and I'm going to look at this area. Not just underneath these curves, but this shaded in area, just the stuff in between. How do we find this area? This area is a little bit different, but what we'll notice is that really what it is it's the total area under this f function, our orange graph, but we're going to subtract this gray portion. It's like if we colored the red all the way down to the x-axis and then took out the stuff shaded in gray, which really then we're noticing it's the full area under f minus the area under g. And so we're really going to be subtracting two areas or subtracting two integrals. If you want, though, we can always just look at the functions themselves. So here's our theorem that we have. If f and g are continuous functions, they both have to be continuous, because if there's any asymptotes or things like that, things can get a little crazy. And f of x is greater than or equal to g of x, meaning f of x is on the top and g of x is on the bottom over this whole interval. Here's our starting point and our ending point. Then the area bounded by this curve here on the top, this curve here on the bottom, between these two things, is really just the difference of these functions. You could also say it's the difference of these areas. So we could look at both of these integrals separately and subtract them. But most of the time we'll be able to combine these functions together nicely. We shouldn't get too worried about the actual letters f and g. You'll notice that in this picture I did use f and g, but really what we want is the top function minus the bottom function. So we have to keep this idea in mind. So really this is kind of how our integral gets set up. We're going to use whatever that left end point is on the bottom, and the right, let me fix that, that's a little messy. The right end point on the top here, and then we're always going to do the top function minus the bottom. So don't get too caught up with the letters f and g. Sometimes they'll be called h or whatever. Sometimes g will be on the top of f. All we care about is that one function is on the top, one function is on the bottom, and we're always going to do top minus bottom. Other than that, it's pretty easy. We'll talk about a couple of harder tricks that we have to look for in class, but for now, let's just get the basic setup here. So here's a nice graph. I've already gone and drawn two of our pictures. This red graph should extend a little bit so we can see what's going on. But what we're going to do is look at the area from an x value of -2. So we'll go all the way down here up to an x value of 1. And we could kind of imagine this red graph still decreasing down a bit. Anyways, when we go ahead and shade in this area, you'll notice that our starting point on the left is -2. Our ending point on the right is +1. The blue function f is on top, and the red function g is on the bottom. So when we set up our integral, this is what it's going to look like. We're going to go from -2 to 1 of our blue function, half x plus 3, minus our top red function, -x squared plus 1 dx. Instead of splitting this into two integrals, we can go ahead and just combine this all together and get the integral from -2 to 1 of now positive x squared, because we have a negative and a negative, plus half x plus 3 minus 1 is going to be 2. We can do our fundamental theorem of calculus and say we'll find an antiderivative. That's x cubed over 3 plus half x squared over 2 plus 2x, and we're going to evaluate this from -2 to 1. So we'll put 1 in first. So we've got 1 cubed over 3 plus 1 squared over 4, 2 times 2, plus 2 times 1. And we'll subtract that when we put in -2. So we'll put in -2 cubed over 3 plus -2 squared over 4 plus 2 times -2. So we've got, let me grab my calculator and throw all this stuff together and we'll see what we're looking at. All right, so we've got 31 over 12 minus -17 thirds, which gives us 33 over 4, or 8.25. 8 1/4 square units. That's the size of this area here. So again, we're just going ahead and combining these things together, and now it turns into a regular fundamental theorem of calculus example where we have to find an antiderivative, plug in our top number, plug in our bottom number, and subtract those answers. Let's take a look at another one. So here we want to find the area bounded by these two graphs. F is in blue, G is in red again. Now you'll notice our red one is on the top though. So the integral when we set it up is actually going to go from 2 to 4. In this case, G is going to be on the top because it's red. So we've got x plus 1 minus our blue f function, -x plus 1 dx. If we want to draw this to really see what's going on, we've got the area in between an x value of 2 and an x value of 4. That's this shaded in area right here that we're looking for. This kind of trapezoid shape. So let's see what we've got. The integral from 2 to 4. X minus -x is going to be 2x, and 1 minus 1 is going to be 0. So this is the integral of from 2 to 4 of 2x dx. Our antiderivative is going to be x squared from 2 to 4. So we're looking at 4 squared minus 2 squared. So we've got 16 minus 4, or 12. 12 square units for this thing here. There's going to be a couple of extra little problems. Maybe in some cases we won't know what endpoints we're looking at. So we're going to have to look for points like this here where our functions kind of cross over each other. Or maybe our functions cross over each other, and so we'll have to look at areas on either side of that where it looks like some could be negative. We'll mess around with all that stuff in class. For now, as long as we can set these things up with a top and bottom function from a left endpoint to a right endpoint and know how to use the fundamental theorem of calculus, we should be good to go for stuff like this. So give some of these a try. Let me know if you have any questions.